All right, awesome. So let's go ahead and start off with our 5-4 notes. So the first two examples talk about the remainder theorem. So we're given here, consider dividing 7 and 2. When we divide 7 and 2, we end up with a remainder of 3.5 or 3 plus a half. And each of these components here actually have a name. So we would call the 7 here, this would be our dividend. And this 2 we'd call our divisor. So you might see this as your denominator. This 3, so whenever you have a division problem, your answer is called the quotient. And this half over here is our remainder. And just to kind of keep in mind, this 2 at the bottom there comes from our divisor. Right? So now, moving on. You can see that we can actually rewrite this so we get 7 alone on one side of the equation. So if we multiply both sides of this problem by 2, right? So we're undoing division here, so the 2's cancel each other out. And when we distribute this 2, we end up with 2 times 3, and then 2 times half is just 1. So you end up with that top portion of your remainder, or your remainder, which is 1, right? And so this is important when we're talking about polynomials here. So now we're considering this polynomial where the dividend is f of x, our divisor is d of x, our quotient is q of x, and then our remainder is r of x, right? So you can see how they're kind of set up similarly there. So let's go ahead and look at this definition. Our first definition for this section is called the remainder theorem. And according to the remainder theorem, if we divide a polynomial by a factor x of a, x minus a, excuse me, you will find a smaller polynomial along with the remainder. So you can see here, if we divide f of x by x of a, we end up with x of a times, excuse me, so if we end up with x of a times q of x plus 3 of x, r of x, excuse me, whoa. So now we're looking, and these are all labeled the same thing. So in this case, f of x is our dividend, like we saw in our first example. Q of a is our divisor. We just multiplied it over to the other side. Q of x is our quotient. And then r of x is our remainder. So now we're considering this example, and why this formula works is we can kind of prove it by plugging in a into our x here, right? So if we're given some polynomial x minus a, if we plug in a into x, again, all I'm doing is replacing every x I see in this formula with a. So a minus a is 0. 0 times q of a gives me 0, right? And then plus r for our remainder. So this is kind of why this formula works. So when you multiply the answer to your division problem by 0, you're just left with r. So this is just for those who are curious why we're using this and why this formula works. So let's go ahead and look at our first example. Sorry, I kind of messed around with the notes earlier, so we got markings everywhere. Now we're considering this top section, so we can therefore use direct or synthetic substitution to evaluate polynomials. So applying the remainder theorem to evaluate a function, I'm going to skip over to this last line here, is called synthetic substitution. And we'll look at an example here that they gave us. Oopsies. All right. So you can see here, if we're given a polynomial p of x is equal to x squared minus 4x plus 7, and we're given x equals 5. When we plug in 5 into x here, we end up with 12. But interestingly enough, if we use synthetic division, right, this can be rewritten as x minus 5, because remember, we always change the sign when we use synthetic division. We end up with the same number. We end up with 12 either way. So basically what they're trying to tell you here is if you just want the remainder, you can just plug in a into this formula, and you end up with the same thing. So if you don't like synthetic division and you're just looking for the remainder, plug in the value they give you into your function, and you end up with the same answer. And so sometimes, like in this case, honestly, it's easier just to plug in 5 straight in. But if you look at example 1, plugging in -3 into this long polynomial is going to be a pain, because you're going to end up with -2. Then you have to carry the -3 to the 4th power plus 3 times -3 to the 2nd power. So it's going to be a long process, especially if you do not have a calculator. So it's easier in this case to just do synthetic substitution. Now, synthetic substitution is set up the same way that you set up a synthetic division problem. That's why they have the same name, because they're the same exact steps. So remember here, we don't have an x to the 4th to the 3rd power, so you have to include that. Make sure you include that when you're putting together your synthetic division problem. All right, and so again, synthetic substitution and synthetic division are the same exact steps. You can bring down your -2. Then you're going to multiply. -3 times -2 is 6. Then add. So you get a 6. So you're going to repeat that process. You're going to multiply, then add, multiply, then add. And you keep going until you can't anymore. So -3 times 6 is -18. I add those to get -15. -3 times -15 is a positive 45. When I add these two values, I get 30. -3 times 30 is -90. And we end up with a remainder of -81. So really the only difference between synthetic substitution and synthetic division is that for synthetic substitution, we're looking for the remainder. Your answer is going to be the remainder. So in this case, what we just found is we found the value of f of -3 by using synthetic substitution. So f of -3, when you plug in -3 into this entire function, you end up with -81. All right, moving on to the next example here. So you're given a polynomial, and they're asking you to find the remainder by plugging in this 8 here, right? So same process. You have 8. We don't have any placeholders this time because we have all of our degrees. And we can go ahead and just jump right into synthetic division. So bring down our first term. Then you're going to multiply, then add. 8 times -6 is -48. I add those two to get 4. 8 times 4 is 32. I add to get 5. 8 times 5 is 40. I add to get 9. So really then our remainder is 9. So f of 8, when we plug 8 in or when we use synthetic division, either way you will end up with 9. Alright, moving on to example 2 here. So example 2, we have a word problem here. So we're going to apply this to a real-life situation. The total production of eggs in billions in the US can be modeled by this function, where x is the number of years since 2000, and we got to predict the total production of eggs in 2025. All right, so we're going to use synthetic division again, but with 25 as our x value, right? So I'm looking at this formula up here, and I see that I have all of my degrees, so I don't need any placeholders. And it might look scary because we have a bunch of decimals, but you have a calculator, so I would definitely utilize that. So I'm just doing the same steps that we did for the last two examples. I'm bringing down my first term, and I'm going to multiply, then add. So 25 times 0.007 is 0.175. I add those to get 0.026. Multiply again. Then add. Multiply. Then add. So I have these values written down already. That's why it makes it look like I'm going fast. But if you use this with the calculator, you might be going a little bit slower. That's totally fine. And so they want our answers in billions. So this is our remainder. Therefore, approximately 139.355 billion eggs will be produced in the United States in 2025, which is a lot of eggs. So we're going to skip this next example because we didn't do it in class. And we're going to jump straight into example 3. So example 3, we are factoring polynomials, right? So when a binomial evenly divides a polynomial, the binomial is a factor of the polynomial. And we've heard this word factor before, and its definition has not changed. So if you're looking at 35 divided by 5, for example, you end up with 7 with no remainder. Therefore, 5 is a factor of 35. So the quotient of this division is called a depressed polynomial. Depressed polynomial. Sorry, I got distracted. Yeah, we got some people outside here. Okay. Let's jump right into the first example, right? So we have a depressed polynomial. So again, if we're looking at this first example down here, our quotient, because we have a remainder of 0, this is our depressed polynomial. All right, so the depressed polynomial has a degree that is one degree less than the original polynomial. And we've seen this before with synthetic division, right? When you take the quotient of our synthetic division problem or the answer to the division problem, we know that the degree is always 1 less than what we started off with. So let's look at the first example. So really, this is exactly like synthetic division. Now, if you see this problem and you're trying to find the factors, you might recognize that, well, we've done this before. We found factors before, but we use grouping. However, when you try to use grouping with this problem, you factor out an x to the second power and then a -1. And you can see when you get to this step, your parentheses don't match. So you cannot solve this using grouping because, again, our parentheses here need to match. In this case, they don't. So we're going to erase this here. So this is why they gave us one factor. And with this one factor, we can find the rest. So just keep in mind, though, that when you're dividing, we use synthetic division, right? With -8. So we're going to do -8, right? I have all of my degrees, so I don't need any placeholders. And I drop this down. I'm going to multiply, then add. All right, so -8 times 2 gets me a -16. I drop that down to get -1. -8 times -1 is 8. I add to get -3. I multiply again to get -24. And I add to get 0. And I know I did something right because this is x plus 8 is a factor. They told us it's a factor. So I know for a fact that my remainder should be 0. So then our polynomial here, our depressed polynomial, would be -2x squared minus x minus 3. And now when we want to completely factor this, this is 3 terms and it's to the second power. So it's possible, there's a big possibility here that we can factor this down even further. So we're going to go ahead and try. So I'm going to use Lizzie's method here. we're going to find two numbers that multiply to negative 6 and add to negative 1. In this case, we have negative 3 and negative 2. So we have x minus 3, x minus 2, and we multiply the 2, so we gotta divide the 2 out. The first one doesn't simplify, so we end up with x minus, 2x minus 3 and x minus 1. And then they're asking for all the factors, so I'm going to include this x plus 8 here. Right, and I got this x plus 8 from our original function, because remember, that is a factor as well. All right, so let's look at the next one. The next one, this next polynomial, we have all of our degrees, so we don't need any placeholders, so I'm going to jump right in. Then I have 3, 10, negative 27, and negative 10 as my coefficients. Drop down my 3. I'm going to multiply, then add. 2 times 3 is 6. I add to get 16. I multiply to get 32. I add, multiply, then add. So then my polynomial here is 3x to the second power. Remember, it's 1 less than what we started off with, plus 16x plus 5. So similar to the last one, to factor this, you need to use, it's in quadratic form, so I'm going to just go ahead and use the Lizzie's method. You can also use a British method, whatever you're most comfortable with. I know that 3 times 5 is 15, so I got to find numbers that add to 15 and multiply to 16. In this case, it's 15 and 1. So now to finish this off, I get x plus 15 and x plus 1, and I got to divide out a 3. So I end up with 3x plus 5. Oh, no, I don't. The first one factors out, actually divides out pretty nicely, so I don't even need to slide. I just end up with x plus 5 and 3x plus 1. And then don't forget the polynomial that we started off with, so it's an x minus 2. There we go. There we go.